Empezamos entonces.
La que Helen no nos dé la señal. La directora, ahora sí.
Bien.
Le pedimos a los de Zoom que nos digan si se escucha bien por el chat. ¿Es posible? Bueno, yo estoy medio lejos. La gente que está conectada al Zoom. Ok.
Ay, estoy acá atrás y se escucha bien. Perfecto. Marcelo, cuando quieras.
Muy bien. Bueno, muchas gracias, Helen. Buenos días a todas y a todos. Estamos muy contentos de recibir en Montevideo hoy a Ligia Scott. Primero que nada, quisiera agradecer a la Comisión de Seminarios y a Goyo y la Ola que accedieron muy amablemente a cambiar una actividad programada para aprovechar la estadía de Ana aquí en Montevideo. Entonces, bueno, Ana está participando con nosotros en un proyecto Cabio, donde la idea es identificar compuestos antiinflamatorios en el marco de COVID-19, y en el marco de ese proyecto colaborativo es que tenemos la suerte de tenerla aquí en Montevideo. Ana es profesora asociada 4 de la Universidad Federal de ABC, asesora de maestría y doctorado, es líder del Laboratorio de Biología Computacional y Bioinformática de la Universidad de ABC, tiene una beca de productividad nivel 2, becaria postdoctoral en la Universidad de Pittsburgh, y también fue becaria postdoctoral en el Laboratorio de Biología y Farmacología Aplicada en la prestigiosa Escuela Normal Superior de Caen, en Francia. Fue doctorada por el Departamento de Física de la Universidad Estadual de San Pablo y en los últimos años ha trabajado en el desarrollo y aplicación de métodos híbridos, combinando modos normales y dinámicas moleculares para simular sistemas de macromoléculas, que es básicamente lo que nos viene a hablar hoy. Así que muchas gracias, Ana.
Myself, thank you for the nice introduction. I will talk in English because I don't speak Spanish, but I can speak Portuguese. Okay, I will not talk about this project of Cabio about COVID, but I want to talk about a paper that we published recently, and that we compare these hybrid methods, and we discuss what is the advantage to use these hybrid methods and doesn't use molecular dynamics or traditional methods. And then I hope convince you to start to use these hybrid methods. Okay, if we look for the biology paradigm, all the time we think you have a sequence. The sequence applied in the structures is correlated with the functions. But in the last 10 years or 20 years, we know that we have another element that is the dynamics of the protein. No, these movements intrinsic for the protein, they are very important for the function, for the structures, and they are influenced by the sequence, by the structures, and they are correlated with specificity of the protein, allosteric transitions, motions of domain, diffusions of ligands, and the hybrid methods. They are a good approach to study this kind of movements that is very important for the function of the protein. And remember that the protein is not something like static or a picture static, but it's if you look for a protein, you have an ensemble of conformations, and inside of a small energy range. Then and this fluctuation of conformation is very important for bind ligands or interaction with other proteins. Okay, and what we have doing in our lab in the last this is about the movements of proteins. If you look, if you think about the movements of proteins, we have the fast movement is the hydrogen bound vibrations around of 0.1 or 1 picoseconds in biology time, not simulation time. And if we're thinking about the breaking the hydrogen vibrations, and if you think about the breaking this hydrogen bonds, we are talking about 10 picoseconds, between 1 and 10 picoseconds. Looking for the collective motions of waters, we are around 100 picoseconds. And if you want to see large motions or collective motions, when we have a domain closed and open, significant conformation changes, we are talking about microseconds in biology time and biological time. Then what we argue that the hybrid methods, they are very efficient and they are fast to find these collective motions and to study this kind of motions, that it's a slow motion and with a low frequency. And sometimes it's hard to see this using standard molecular dynamics or another traditional methods, okay? And these are another kinds of motions, are local motions, and the frequency is high, and they are fast motions, okay? We know that we have many experimental methods that can be used, direct or indirect way, to study these motions and these conformations, like crystallography, NMR, microscopy, electronic now, spectroscopy, calorimetry, and we can do many trials to understand these conformations. And we have many approaches to simulation and traditional molecular dynamics, and I will talk a little bit about hybrid methods that combine use elastic network models or normal modes analysis combined with molecular dynamics. Okay. And just this is a simple example to show how it's important to think about these collective motions in these conformations change. If you have two proteins and the interaction between two proteins, we have the folding channel of the energy profile of the proteins. What's happened? If you think about the model lock and key, that is our old model, you will have something like that. You have the protein, the minimum, and the other protein or the other ligand bind here, and okay. But this is not a good model. If we can understand better what's happened in molecular details, we think about the combination of these two models, where you have your protein, your receptor, these fluctuations between many conformations, and after you bind with the other protein or with a ligand, they change, they induce a fit, they change the structures. Then you have a just of this conformation. Then this is just one example of how this, and it's an old paper, but how this kind of aspect is important if you want to study the interactions with interaction of proteins with another proteins or with another ligands or peptides. In the last 8 years, our lab has been specializing in research about these motions and this conformational change of macromolecules. As Marcel talked, we help two groups, one in France from David Perraya and another in the United States of Yvette Bahar to develop, to improve, and to apply these methods. Usually to study molecular mechanism of some proteins involved with diseases like diabetes, HIV, now COVID, and some Parkinson. Okay. This is an overview about these methods. Okay. If you look here, you have the core of the methods. What is the base of the method? Then here you have the methods based in force fields, full force fields. Here you have based in MEG simulations, molecular dynamic simulations, or elastic network models, energy minimization, Monte Carlo, Browning, haptic exchange. Then you have many hybrid methods proposed in the literature. And these methods sometimes can combine different techniques. For example, we in this moment, we work a lot with this method, MEDNM, molecular dynamics with state normal modes, was developed by the people in France together with Ligia Scott in Rio, and now was improved by a student of PhD after postdoc of our lab, Pedro. And what's the idea of MDNM? You calculate the motions of the protein, and you take a set of motions, modes or motions with low frequency, and you can combine or can use just one. Then you do many replicas, and you state this each replica many times in the direction of these modes or the combinations of the modes, putting a small temperature, like you increase it 3 kelvins or 5 kelvins, depends of the system, and after all excitations, you allow the system stabilize equilibration. Then you can sample the space better than a traditional molecular dynamics. Then we use molecular dynamics, but combined with all atoms field, force field, or with you can use with elastic network models too. That is a coarse-grained model. If you have a huge system, you can use this option, or if you want to see mutations, effect of mutations, or you have a small system, you can use force field, a complete force field. Okay, then we use this is another method, but it's oldest method than this MDNM, but it's fast, and sometimes we use it to sample the space, and after use this conformation to do a virtual screening or a docking, or to have a initial picture of the structural dynamics of this protein after we refine it with this method. And this co-MDA is another method we have been using too, and I will talk about this fast, some results about this. The emoji, MDNM, cluster NM, co-MDA is based in elastic network models and Monte Carlo. And he used some minimizations too. And now we use a short molecular dynamic simulations too. Cluster NM, it's a simple method. What's the advantage of this method is that we can use the water, spaced water, you can put, but here you don't have spaced water, and here you don't have spaced water too. Okay. But some examples of where this method had been used. The cluster M with a dock has been used to study the interaction between protein and protein DNA. COMG, it's a good method to see the pathway between two conformations. If you have an initial conformation and a target conformation, the COMG he will find the best way to start from here and arrive in the target using the motions, the collective motions calculate, and he will select the best motions and will create new conformations until the target. And like I think Philippe, I was talking to Philippe yesterday, and he was talking about some pictures from cryo microscopy. This COMD is a good method for this, because you can have many reference points along the way. Then you can generate the other snapshots of along this pathway. And there are some methods, I never used this SCM, but he's been used with SACs to refine some experimental data. And MDNM is a method that we have been using in the last years. You can use to sample the space of the conformation space, but we have a new version of MDNM and MFIT that is to refine cryomicroscopy maps and adjust the structure and have a structure with better resolutions that can be used for this to have a good template. And what's the I didn't talk it, but what's the idea of the the normal modes is different from if you have molecular dynamics and you have a time, and you have the coordinates, and you have a trajectory, and you have energy profile, very, very complicated, complex. When you have the normal modes, you consider that your protein is, or the complex is in a minimum, but don't necessarily to be the global minimum. Should be a good minimum. Then otherwise it will not converge. And then you calculate the Hessian matrix, diagonalize, and you have the aging values and the aging vectors. And the age vector is the direction of the motions, and the age values is the intensity of these motions. Then you have two coordinates, okay? And you have the frequency, the motions, then you don't have time. And it's fast than molecular dynamics, and sometimes not because just the velocity of the computations, but it's important because sometimes you run along molecular dynamics, but you cannot see our collective motions, and with this kind of method we can find these collective motions. This is just an example of how the mode worked. We after calculating the motions, we display the structures 0.1 or 0.2 angstroms, and we run a molecular dynamics with low temperature and this force restraint of force field. Then we try to keep the trajectory of the protein in the minimum, but we generate many structures not in the minimum, but close to the minimum energy pressure. Then you can sample the conformational space. Now, this is about MGNM, but I don't know if I spent many times with details, but what we have a combinations of normal modes and molecular dynamics. You give a PDB, then he will calculate the modes, he will store that coordinates of the modes, and after he will state these modes along of a combinations of 1, 2, 3, 4, or 20 modes. How many modes do you want? Usually, it's not necessarily much modes. Usually, the most system I will show you 4 examples. 3 modes, it's enough to sample the collective motions. And then you run a molecular dynamics. You put a delta temperature like 3 or 5 or 7 or 10 kelvins. You can it's a parameter. Then he will state these structures and generate a new structure. And he will do this many times in many stations. The number of stations is a parameter. You can usually we use 10 or 20 stations for each habitat, and usually we start 2,000 habitats. Then you generated 2,000 structures, or you can, if you start more habitats, you generate more structures too. Then, okay, what we did in this work is we tried to compare these methods, CoMD, MDNM, cluster AM, standard molecular dynamic, free molecular dynamic, and experimental structures. And we select 4 systems, and very well known, we know the behavior, and there are many experimental structures, and there are many papers in the literature. HEV protease, HEV transcriptase reverse, Timberl, and PGK. Okay. Then after we define the parameters to classify open and close the structures. Then about protease, we use the distance between these 2 residues. That is, you can measure if it's open, the flap, or closed. About TIN, we use the distance between the catalytic loop with these two residues in the both chains. And about PGK, we use the distance between these two residues. And about the HEV transcriptase, we use the distance, the angle and the distance between the fingers, and this another domain. Okay. And then we run these methods, and you search for experimental structures. Okay, then about the experimental results, structures solved, HEV protease, we find more than 700 structures with 9%. For the PGK, we found the 35 structures, for team 67, and for transcriptase more than 300 structures. This is a similarity, or they not similar, yeah, the similarity of sequence of of these structures. Then okay, we thought, okay, this is a good number, then we can use it. Okay, after to compare, and we run both methods, and we run the standard free molecular dynamics tool, a standard molecular dynamics tool. I don't know what's that. Sorry. I'm not sure. Thank you. Okay. This is the parameters of the simulations. Then we run we use 3 modes for the first 3 modes for Cognition, the first 3 modes for cluster NMD, the first 3 modes for cluster NMD, that's a extension of cluster NMD, and the first 3 modes for MTNM. This is the number of replicas that runs. Why we use just one run for MTNM? Because MTNM will generated a large number of replicas, and each replica can correspond is an independent simulation of the other replica. Then we don't need to run more than one. Here we have about, I think it was more than 2,000 replicas. Okay, this is the number of conformers generated by each method for protease, PGK, TIM, and transcriptase. Then we have these numbers of structures generated to compare with the experimental structures in the MEG, the free molecular dynamics. Okay, this is some results for transcriptase. If we have, then what we look the state of the protein, open and close. Open, this is dashed line is a open and close state according that distance that we define. Okay, then we look how this method is sampling the structures around this closed and open state. Then if you look at the experimental structures in PDV and the MEG, MEG doesn't sample in the open space, but in the experimental data you have more open structures and a small number of closed structures. If we look for here cluster dynamic and the station of this method, we have a good sampling of the open state, but it's not good for the closed. And it's the same for co-MEG and MEG. MTNM finds some structures in the closed states, but it's a small number. I don't know if it's possible to see, but you have a small number here. Then it was the only method that find the closed state. If you look for the RMSD with the initial structures, if you compare molecular dynamics and experimental data, you have this. If you compare the methods, then you can see that MDNM is sampling a large space, but sometimes this is good, but sometimes it's not good, because sometimes you have some structures that doesn't correspond to the biology structures. Okay, then we need to analyze this with some careful. This is here we project the structures around the 2 first PCAs. the two first motions for MEG, MGNM, co-MEG, cos-NM, cos-2C, and this point is the open, it's the open structure, the initial structure, okay? And here is we created this Mathematica. It's this Mathematica measures what's the desviation of the experimental PCAs to define how many modes I need to characterize the motions of this protein or the space of this protein. Then if you look, there is a difference. Sometimes you need 3, sometimes you need 4. I will show some details. Or sometimes you need 5 modes. And this is the Pearson correlations between this is the root mean square fluctuation of the for the structure generated by the methods. Then you can see that the MEG and the experimental results will have a RMSEF lower than the others. Then here you have the correlation, but something good is that if you but something to highlight is if you look for MEG correlation with experimental results, you have 0.767 correlations. If you look at the other methods, hybrid methods, you have a better correlations with the experimental RMSF. That's important, okay? Just sampling the space. This is the first 3 PCAs for transcriptase, because if you look here, for transcriptase, I don't know if it's possible to see, we just need three modes. Okay, all methods with 3 modes. After, it's not important. We don't need. Then this is the 3 first modes for the. Here is the experimental from the structures in the PDB. This is from the co-MEG. Then you can see the 2 first modes. You have a good correlations. The 3rd mode you don't have a good correlation. Okay. But you can consider this as a good result. This is for chain burial, and now we need 4 modes. Then the number of modes that we need to sample in the space depends on the system, the structures, and you can see that the co-MEG and MEG sampling very well the closed and open structures. If you look for cluster and MEG2 and MEG experimental, MEG doesn't simply have a good confirmation here. You have experimental structures, but not a good sampling from the MEG. Okay. And in this case, because chain has a very well-defined open and closed states. In this case, the hybrid methods have a better performance than MEG, like the other transcriptase. Then, if you look at the correlations, we have the correlations of experimental with MEG and the other methods. This is the projection of the structures. Okay. And if you look for the modes, we have that the modes 3 and 4 has a good correlations, but the first mode and the second mode, there's a correlation less than 0.6. Okay, according to Pearson test. If you look for PGK, we have similar results, but here again, the MEG has a very difficult to find the closed structures cluster and find very well the structures. MEG and M fine, co-MEG fine, but okay, but you have a high number of experimental structures in this state closed. This is the fluctuations, the flexibility for each method and for the experimental results. And here is the correlation. The correlation is good. In this case, we need 5 modes to characterize the space of the protein. And the mode 1, 3, and 5 has a good correlation, higher than greater than 0.6, but the mode 2 and 4 doesn't have so a good correlation. Okay. And if you look for protease, we have to now here we have some difficult to find the closed structure protein D2. No? Then if you look all the time, the hybrid methods they sample a large space than the MEG, and sometimes they find both states better than MEG. Okay. This is the same for protease. Then the two first modes was good, and no, sorry, why the number? I didn't explain something about this. In the first two cases, these numbers was the same, but not here is not the same. Sometimes the number of the modes just are then you have, for example, the mode 1 corresponds to the mode 3 or 4, the other structures. Okay, then sometimes this number is not the same. The important is how the number of modes that has a good correlation. This is the most important point. And this is a resume of the results. And if you look for here we have the methods. Here we have the closed distance in angstroms. What is the closed distance? It's a distance less than 1 angstrom. Is the closed distance between if you take this is the distance that we are measuring for the states closed and open for each system, but compare with the experimental structure. And it's wrong here because in both just this should be just the structures with less than 1 angstrom of difference. And if you look for experimental, you have the distance is 21.5, the average of distance. If you look for co-MEG and MEG here, you have less than 1 angstrom of compared with this difference. If you look for the team, then you have many methods with less than 1 angstrom of difference from the experimental structures. Okay, and then we can see that these methods has a good performance. Okay, this is the minimal RMSD from the closed structures, and then we can see in both the better results. Okay, and this is that another criteria about the experimental PCAs. Okay, that equation where we calculate how they are the deviation of these PCAs. Then what we try to conclude with this work is that we know that this kind of hybrid method is increasing the literature, and we can see that you have the overall breadth of the conformational spaces predicted by these methods is larger than what we observe with experimental structures and MEG simulations. We have good results to find the closed and open structures. Then you could find the open and closed for protease, for transcriptase, then using that metricas. Okay. Then what we are recommending that this hybrid method is an efficient technique to sample the space to find meta states open and enclosed. That's important for interaction or for the functions. And sometimes you cannot detect these states with free molecular dynamics or another kind of method. And what is the main challenge is capture better the closed conformations. Usually the conformations that are not entropically favored, because sometimes you have the closed state, but entropically is not so favored, then the method cannot find. And I didn't say, but we start from the open to the close. We have the open, we don't apply the closed structures, okay? Then this, now I will show some videos. This is the motion for protease with the four methods. Okay. This first for MG, so sorry, for with the four PCAs. Okay. The first four PCAs. I will put here. It's possible to see the flap closed and open very well. This is for the four system. Each method for the four systems. For the protease, you can see the flap very well. And this is the cluster NMG for the systems. This is cluster NMG. And the other video for CoMG I couldn't find in the drive. I'm sorry. I will talk a little, I have 5 minutes, and then I will talk a little bit about another work that we apply this MDNM to study a channel that is the human dopamine transport, to find the metastates and to see the stability of these metastates and the transition between these metastates. If we look for the human dopamine transport, it's very well known that we have in describing the literature, we have 4 states: open, awful, OFC, all occlusive, and open. That is these states. The transition between states is that. This state is important for the transport of the dopamine inside of the cell. And there is an experimental report, experimental paper that say that sometimes if you change the phosphorylations in these sites, you increase the influx or you decrease the influx of the dopamine inside of the cell. And what we try to show that why this happened, okay? Then we look, and then the first point, how we will define, which metric we will define that state. So awful, OFC, and close it. Then we can use many metrics. For example, for awful, you can use the far distance between the segment, the transmembrane segment, or you can use the distance between 2 residues. Then we use the combinations of 2 metrics in this case. And what we try to see about this experimental paper, it's an old paper, but it's very interesting. They say that if you have all these residues phosphorylated, should be the references to. If you have the serine 12 not phosphorylated, you increase the influx. If you have the serine 333, you decrease very well the influx. Then we try to see why this happened. We apply the MDNM, but I will not talk here because I talked before. Then here is the projection of the structures that we find in the states for cases. And no, we don't have any citrus is not phosphorylated. All citrus are phosphorylated. This is the reference. And serine 12 not phosphorylated, and serine 33 not phosphorylated. If you look, when we have in the reference system, we have good populations for all states. Okay, and the green is the minimum, the structure minimized. If you look for the when you not phosphorylate this serina 12, you favor the open structure, the off structure states. Okay, and if you don't, and after if you phosphorylate the serina 12, but not this, you favorite the all structure that is closed state. Okay, and here if you don't phosphorylate any sites, then what you can see that yes, if you phosphorylate or not phosphorylate just one residue, you have a tendency to have more one state or another state, and this could be correlated with the flux. After we look for the RMSF and the correlation between RMSF to the four systems, and if you look our system has a good correlation with the reference, but this, when you reduce the influx, doesn't have a good but lower correlation. And then after we calculate the free energy for using the sampling, we calculate the free energy, and here is the projection. And if you look here again, if you have the all phosphorylated sites, you have a good populations in the minimum, in a good range of energy, around 1 kT or 2.1 kT or 1.5 kT, and around the minimum. If you have the serina 12 not phosphorylated, you have more structures off in the minimum. And here is the same, is the opposite. You have the closed structures more than this. Both are closed in the minimum. And if you don't have phosphorylated, you have this situation. Then okay, this is good because you are having more energetically. You have more states. Then we calculate using Markov chain the probability of the states for each system. And this is the probability of the states of the system and the probability of transition between the states. Okay. Then we can see that in this case, water is more stable. And now we are doing a simulation with these systems, but putting the dopamine in the off of C and IFO and all states, and push the dopamine, and we can see, I didn't bring you the results, it's initial results, but we can see that for this case, it's more easy for the dopamine cross the channel. You have different interactions, and it's fast. You need less force to push the dopamine. In the other case, you need more force. Then we are trying to correlate it or what? And I didn't show the motions. If you look at the motions, the modes change too for the now system. Then what we can try to conclude in the next work is that if you change the phosphorylation, you change the motions. If you change the motions, you change the population of the states. And if you change the population of the states, you change the probability of you find that structures in that state. And after you have more human dopamine transport in our off states, and the velocity and it's easier for the dopamine inside. Then you increase your influx in the cell, and otherwise you decrease. And why we are doing this? Because it's now after we can say we know that the alpha-synuclein, it's a modulation of this channel. Then, and the modulation of this channel is very important for Alzheimer, because if you have a high concentrations of dopamine in the nervous cell, you have a stress oxidative, and you damage the cell. Then we are trying to understand this mechanism using these hybrid methods. Then until now, we think that's working well. This paper was accepted now in the proteins with a minor review. Then, okay, this is that I would like to show. This is my team. It's a small team, but it's a good team. I have a system research, a postdoc, for PhDs and a master student, and many collaborators. This is very good. And thank you.
Thank you, Anna, for this nice talk. So we can move to questions and comments.
Thank you very much. All this kind of comparison with different methods, I think they are very useful for people in the community to select the best one. And just a couple of things I couldn't understand very well. When you said that you compared all this set of experimental structures,
yes,
in some of those cases, they are for mutants in the product.
Now we select structures without mutant. We use some parameters to select the experimental structures.
Okay.
Search, because just one mutation change the motions. Yeah. We try to find just wild type. Yeah. We put some parameters, the resolution of the structures, mutations, and something like that.
And have you checked also for different symmetries in the crystals, or like selecting just?
No, I think we didn't look. It's just mutations.
It's just out of curiosity, since you said that you can sample with some of the methods, you can sample better open or closed conformations.
Yeah.
I wonder if this is more or less allowed in a given symmetry, in a given crystallographic packing. That you can see or not see.
Okay, this is nice. We didn't see this. Yeah. But it's a good point. Thank you.
And may I have another one?
Yeah, sure.
In the selection of the normal modes, that you say, I mean, in some cases you need 3 or more. You just set the cutoff.
Usually more than 5, I think is not as, we just use more than 5 for one case, but it's a different case. We have the prion, then we want to show the transition between the not infectious to the infections form. Then we start with small number of modes, doesn't work. Then we put more than 40 modes, because we need local motions. Then in this case, we need more modes. Then work it. We don't find the complete infectious form, but we find an intermediate structure close to the infectious. She starts to change the secondary structure for beta sheet. And after we calculate the free energy of these structures. But if you want to see a phenomenon that you need local motions, you need to put modes with high frequency too. Then the methods allow you put how many modes do you need. But to see close and open or great motions, global motions, then more than 5 usually is not necessary. And what we can use, and this parameter this metric that we create is good too, because after calculate the modes before the hybrid, to apply the hybrid method, just after the calculate the motions is the first step. We can check the standard deviations of the PCAs. Then this is a good reference for you select 3, 4, 5. Sometimes if you put more than you need, it's not good. We have this effect in our system. we start with many modes, then you can see nothing good, because sometimes you have like noise or something. Then you need to try to put what is the number, the necessary number, not less than no more. Okay, but this is a good. This was the first time that we used this Matemática. I think we was doing the analyze the results. Then we tried to find the Matemática. And this is a good Matemática. I think it worked very well.
Anna, you have shown several examples, but I wonder whether there could be some, with your method, some limitations depending on whether you have transmembrane or soluble proteins or large or smaller proteins. Can you think it's a broad method or?
No, the semi-DNA you can use with membrane, with everything. In the dopamine, in this results dopamine, we calculate with everything in the system. We have the membrane, we have water, split water, we have ions, we have everything. The mode is not possible to use the membrane. I think the COMG you can put the membrane, but then you have yes, you can put COMG and MD, and you can put the membrane and water. The other methods, I think, no, just increased water. You don't have membrane. And if you have a system with membrane channel, I suggest the MD and the better system, the better method. I think you have a question.
Yeah, this is a very naive question because I work in a different field, but you mentioned that when studying the open and closed conformation that one of them was not entropically favored. So I was wondering, in situations where there is only one molecule on water, how much the entropy governs the dynamics in comparison with...
Okay, what we call it entropy conformated, it's around the number of the population. Just, it's not entropy. Entropy is just a state density. It's just a number of structures in that state.
Okay.
Yeah, it's we shouldn't use this term.
Okay.
Because we calculate the energy in the yeah.
And there are several parameters that can regulate these motions, right? So, I mean, I don't know, translational modifications, mutations.
Translation, mutations, yeah, so translation mutation change a lot. And yes, I think it's that. But if you have a ligand change, ligand, a small ligand, or a cofactor could be important too. For example, in the case of HTP protease, if you look at the structure, usually you have crystallographic waters. No, if you remove this crystallographic waters, it's not good. It doesn't work. Then you need to use the crystallographic waters, and this kind of detail is very important. Change the motions. Yes. We have two papers about the protease. It's old papers that we show that this motion. The motion of the flaps. If you have just we use data from HIV patients, then we show that there are some mutation. Just one mutation is not in the flap. Change the flap, change the motions, and after we use it, it's from patient data from United States that was using a treatment for HIV, some drugs. then we show that this mutation changes the motions and the drug escape for the bind site, the inhibitor escape. And after we use patient data, but with a double mutations. And the double, the first mutation is interesting because it changes the motions. Some and the inhibitors can escape, but the catalytic activity is low, and it's not good for the virus. When you have the second mutation, the catalytic is recovered, but the motions keep changing. Then he can escape sometimes, but he has a good catalytic, a normal catalytic efficacy. Then yeah, but I think phosphorylation and some kind of cofactors or in mutations change a lot.
Questions?
¿Algún question?
No.
Okay.
Te agradecemos mucho la presencia y bueno, esperamos que